Okay, this is for problem 2.2 of Wald's General Relativity, where he wants us to prove that for any smooth function f mapping from R into R, that we can write it in the form of equation 2.2.2, which I've got on the right-hand side here. So we're not going to use the hint where he gives us an identity and then asks to prove it for general n by induction. Instead, we'll derive the n equals 1 case, and then the general n case becomes somewhat obvious after that. So we can start by writing down our fundamental theorem of calculus. So just f at b minus f at a equals integral from a to b f prime x dx, which is a mapping from R1 to R. Now we're going to kind of work towards the identity that he offers us here. So let's make a rescaling where we let x equal t b minus a plus a, which means that dx is just b minus a dt. Now this rescaling is going to change our integration limits too, so let's just star the relevant equation here and plug in a and b. So if it's a, then we get equals t b minus a plus a. The a's on either side end up canceling, and then the only way this is true without the trivial b equals a case is to say that t is 0. And then similarly, if we plug in b, I'm just going to bring the a over to the left side immediately here. T b minus a, and then again, same thing. Unless this is trivially true, it implies that t equals 1. Okay, so we can rewrite our fundamental theorem now in terms of our new rescaled variable. So this is going to look like this. F at b equals f at a, which I'm just pulling to the right side, plus 0 to 1 f prime of our rescaled variable here. So this is t b minus a plus a times b minus a dt. And so now we can pull the b minus a out front. Times this integral. And now we're not going to attempt to evaluate this because we don't know what f prime actually is, but we can just give this a name, right? So we're going to define it to be h1 of b right now. And now we could rewrite this entire thing here. But when we do so, let's switch b and just call it x now, just so that we get ourselves closer to the notation that the problem's looking for. So we'll go ahead and rewrite this as f of x now equals f at a plus x minus a h1 of x, which is already feeling kind of close to that form of equation 2.2.2 that we're working towards, if you remember up in the top right here. In the case where n equals 1, obviously, this is right, because this sum only has one term then. Okay, so we can move on now to the more general n-dimensional case. And to do so, we'll start with our multivariable fundamental theorem of calculus, FTC. So let's write it down this way to begin with. So f at b, which is a point now. Where am I on my paper? Right, there we go. F at b, which is a point now, is f at a plus this integral of nabla f dot ds. And remember, what we're trying to show is that fn of x, the n-dimensional mapping, equals f at a plus the sum to n of like x mu minus a mu h mu x. So if you compare the fundamental theorem to the right hand side. Obviously we already have the f at a term, so really all we have to prove here is, I'm going to get rid of this line, all we have to prove here is that this integral can be written, oh my goodness, nabla f ds can be written as this sum over mu up to n, x mu minus a mu h mu x. So this is what we want to show. If we can show this, the proof is done. Okay, so let's expand this term, the nabla f ds, in terms of the chain rule. And in doing so, we're going to have some integrals look like this. So we're going to go from a1 to b1 of del f by del x1, we'll say, dx1 plus a2 to b2 del f by del x2 dx2 plus dot 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 dot, and we're going to go all the way up to xn in this case. Now what we can do, unless each of these integrals is very similar to the integral we solved at the start of this problem, where we made this rescaling in terms of t. So we're going to do the same thing here, but I'm not going to write it out explicitly. And we're also not going to use the name t anymore. We're going to just prime the variables in each integral. So this is going to end up looking something like this. So the first integral, remember we get that factor of b1 minus a1 out front, and then the integral from 0 to 1 of del f by del x1 prime dx1 prime plus b2 minus a2, integral from 0 to 1 again, of del f by del x2 prime dx2 prime, all the way up again to xn. And what you'll notice, though, is that these are simply, again, those h1, because it's in terms of the variable x1, and then we could call this one similarly h2, because it's really the same thing, but in terms of the variable x2, or x2 prime, I should say, etc. And then so it just goes up and up and up. So we can rewrite this now as a sum, but let's again go ahead and replace b with x so that we are in a notation more similar to what the book uses. So what we're going to end up having is x, actually no, this is going to be a sum right off the bat, mu equals 1 up to n. So we're just summing each of these terms here. And then we have xn minus an times h n x, which is just what the problem, or not what the problem, but what we were working towards. We were able to show that this integral is equal to this sum, and therefore the proof is complete.